morning. This is kind of more of a lighthearted topic, basically some things that we wanted to do to empower our user community. And one of the things I like to have on my little tagline on like LinkedIn or something like that is, empowering user communities is fun. I think if you give the users, some tools they can use to better understand their data and how they're using their storage systems, then they can be happier because they're getting better performance, and hopefully you as an administrator can be happier because you don't have to go around and clean up as much. So essentially, what this is something, taking on Monty Python, just slightly different. We're working with Robinhood here, and Robinhood is a wonderful software product that has been provided by CEA of France. Thank you very much. We really appreciate that. And what Robinhood basically does, if you are not familiar with it, is it is a way to get information about your Lustre file system just by using a web interface, or there is also a command line. So it is already, Robinhood, a client-server model with the web interface to a client. And Robinhood gets its information by using an enabled MDS changelog, and it takes that information, ingests it, and places it into a database. So it's there just kind of for the retrieval without actually having to go back and walk through the Lustre tree. So Robinhood is taking this information and just gathering it from the changelog as the information occurs and storing it in a common retrievable format. Let's see if I can get my forward and back right here. So the next question is, why mess with it? Why do anything differently? Well, the simple answer is because we can, people. We have an environment in which, using a web interface may not exactly be feasible or, even technically possible. We have places where, there are firewalls to certain kind of activity. It's just that it's not always practical to use Robinhood in its original web model. So what we decided to do was to see if we could use Robinhood a little bit differently. We have compute nodes on an HPC that are smaller. Some of them are diskless. They have a little less space for the operating systems. But we do know that getting data from Robinhood is quite a bit faster than actually having to walk the Lustre file tree. So, users might want to get some tasks about, some attributes, or they might want to find out what the largest files in a directory or something are. And Robinhood is so useful for that. Our users really are interested in that sort of data. So, here is the obligatory environment slide. This is basically just showing that our test system for our Robinhood server and a sample client is pretty ordinary. Nothing great shakes here. I will note that these test systems were using the MySQL database rather than the MariaDB. I'll get into a little more of that later. We had a reason for making this change. Our newer systems, ones that are coming in now and everything, are using MariaDB. But this is just kind of, pretty standard hardware, nothing really special. So the first thing you need in order to make this work is to have a Robinhood server on your Lustre file system. So you go about installing the Robinhood software in the usual and customary manner. You have the web server capable. You install the database. You have a database port. We used the standard 3306. And then what we did that was a little different was we established a read-only user on the Robinhood database. We just called ours Robbie. And that user we granted some select execute permissions so that it can actually read the database and access it. And as kind of an optional thing here, we put another index on our database. I'll get onto that a little bit more later. But we tried to, just make it so that we had a way from the Robinhood server that we could actually have some successful connections via the port and this read-only client of the database. So then we have what we are making our compute clients of Robinhood. And essentially, what we did was, being that on HPC systems, you usually have places where you as a user can test your software, install it, make sure it compiles. And then when it goes out to a compute node, often as a user, you don't even have access to log into that compute node. Everything is run through a scheduler of some kind. So we built this copy of the Robinhood software on one of our HPC nodes. And then what we did was we only took some portions of it to send out to our actual compute nodes. So we actually had only the user lib64 library, and we took some of the commands that we wanted to make available to our users, the RBH report, RBH find, RBH du. We did not put the RBH config out there. And we also had a compatible MySQL client that we were able to place onto these compute nodes. And we also had our little robbie.conf. So it looks exactly like your robinhood.conf, except when you get to the bottom, the user ID and password are different for this read-only user. We added the etc robinhood.d includes files, and we also made sure that we put the credential for Robbie if you're using, for example, a .db password. So we had all of these components that we had set up on one of the like nodes of our HPC system, and whether you are using a particular build, a script just to copy the files out there, if you have to take a golden image and then when your compute node rebuilds, it places these bits onto the compute node, however your environment works, that's fine. We just got some of the Robinhood bits out there, but we didn't have all of them. We did not have the full database server. You certainly would not want to be consuming a change log from all kinds of compute nodes anyway. And we obviously did not need the web server bits. So we just took the parts that we needed and placed those onto the client. Optionally, you could even go as far as putting the man pages out there, but we chose not to do that because our users don't really log into the computes anyway. It's all through batch schedulers, so we just kind of left that out. Now, this is a little bit of what we did for our tuning. And the first thing I want to say is there is a website out there on GitHub for CEA HPC for the Robinhood wiki, and it is under the performance_tuning, I think it is. Pipeline_tuning, I'm sorry, it is pipeline_tuning. If you are working with Robinhood and you want to tune it, this is really useful. It explains how you can look at the luster.log produced by Robinhood and look at the stats, and you can see like the times in the fourth column and then the actions that are listed in the first column, and you can see where your particular Robinhood instance might be slowing down. So the pipeline_tuning was really helpful for us. And from that, we were able to find that we were spending more time in our BD or DB apply. I think that's a typo. So we went and we set in the entry processor section on our Robinhood server, and it also was copied into our little Robbie client conf. The max batch size we set equal to 1, so we could process things pretty much as quickly as we could get them off of our MDS system. And we set NB threads to 24, and our stage BD apply max threads equal to 16. For our environment, that worked. Your mileage may vary. It's kind of memory, CPU dependent. It depends on your resources. Those numbers worked for us, but the pipeline_tuning can help you identify whatever would work for your system. And the other thing we did was we edited the etc myCNF file in the MySQLD section, and we used the INODB file format for Barracuda and the INODB large prefix on. Now, this gets into why we had changed over from the default MariaDB to the MySQL. We had to change a mere one line in the RBH config in order to use MySQL versus Maria. Initially, we found that the MariaDB didn't do INODB well. It just did the ISAM, so we went for the MySQL at that point in time. That is no longer the case. MariaDB is just fine with INODB. So this is kind of, you know, an artifact of our particular environment. And we use the file format Barracuda and the INODB large prefix on because we wanted to make another index in our Robinhood database to see if we could speed up some of our retrievals of information just a little bit more. So to do that, we wanted to create this new index on the entries table. And we had to have the two things tuned in the mycnf.conf because otherwise, with the addition of this new index, which we wanted to put in, the aggregate size of the data table would exceed that was allowed by default in the database program. So again, your mileage may vary. So we had this linked, and of course, in order to get these things to take place, we just had to do a quick restart of the MySQL on the Robinhood server. So we had a little more tuning to do. We made the entries row format dynamic. And then we kind of did ours in a batch mode. You could also do it interactively on your database on your Robinhood server if you want. Just to put these changes into place, we created our file class index on our entries table so that we could actually kind of link our FIDs, which is what Robinhood was keeping track of very carefully, with maybe a path name and, you know, some other information there, just a couple. We didn't want anything that was too big. And we just kind of, you know, let that run. We were doing this on a Lustre file system that at the time had over 1 billion entries. And the result was it reduced the time of our RBH report class info query of 2 billion records from 4 hours down to about 20 minutes. So these database tweaks worked for us. So kind of the end result of this, you know, little rework of a Robinhood install is that we now had clients, compute clients on an HPC that the users could actually do a report, RBH report, and find information in -E about a specific file. They could find, you know, the largest file. They could basically get anything that they could get from a Robinhood report command without logging into the Robinhood server, because you don't necessarily want your entire user community with login rights to your Robinhood server. And it did not require a fork of the code. I did not, you know, really have to change anything at all about the Robinhood source code in order to make this little connection, this little query function. We just made it such that on our compute nodes, it just had fewer bits. Again, no full database, no web. We just made it so that it could complete the query actions. So it gave us, you know, Robinhood that users could script, they could parse in a smaller package and from any of, you know, hundreds or thousands of compute nodes. Part of the reason we did this is because in addition to the standard Robinhood functions, we're trying to look a little forward at the user extended attributes that are present in Lustre. In our MDS changelog mask, we did include the XATTR. And that is not a direct query in Robinhood right now, but we're trying to see if we can integrate that for our environment. Right now, we have a general MySQL query that can be run to get extended attributes whenever they're captured. We right now have in our Robinhood setup a policy for most of our extended attributes. So by using Robinhood policy, you can find things that fit the policy description. As I said, eventually we would like to see if we can just get an X attribute query so that we do not have to have an explicit Robinhood policy for each and every X attribute our user community might put in. So if users are looking for files that say, come from the Tyros-N satellite or using, the SSBUV instrument, that can be an extended attribute. And rather than setting up a Robinhood policy for each and every one of those, we could actually just query the extended attribute from the changelog. And being that Robinhood is a nice, neatly packaged, nicely written way in which to get those things. We're working on seeing if we can leverage that, but that's not done yet. I've only just partially gotten started with that. So again, it basically gives more power to our users in order to get information about their system, where files are placed, and hopefully, they can use that information to their benefit to find things more quickly without necessarily having to walk the Lustre tree. Now, I have here just a couple of quick screenshots. Basically, this is just showing a file class, and it has some of the extended attributes in the front for which I have written policies. I just called it, Larko MPI, Larko standard, just an attribute I set manually based on a way in which I had created the data. So that's how it appears if you're actually on the Robinhood server, the way, Robinhood is traditionally written with the command line, on the Robinhood server. And this is what it looks like from, one of the clients with this, stripped down subset of a full Robinhood install. There are some errors up there opening, var log, Robinhood log. There isn't one of those logs on our computes. There doesn't really need to be. I don't see any need of creating one. I don't see a need of giving users permission to read some of these logs. So I consider those messages myself just kind of benign nuisance messages. Not sure that our user community would consider that the same, because sometimes users see messages coming back in their output from their job submission. They're like, but I had an error in it. And it's like, well, yeah, but you can ignore that error. So I would like maybe to see if I can, for kind of the client mode, kind of maybe fix that up a bit, because for a read-only mechanism whereby they're not able to make any changes to the database, they don't really need access to those sort of things. But I can understand how users can find just the fact that they appear in their output annoying. On this one, I had the command run. Again, you see from the root or administrative user, it comes back nice and clean. But that's not exactly how we're going to be using it in this scenario with this read-only Robbie user coming from a client. So that's one of the things that, as I said, with those messages, I want to clean up. The other thing about this second pair of screenshots is that this is from the different versions. From my obligatory environment slide, we had some things that were using my SQL 5.6. We had one that was a MariaDB client. We had another one that was using a Robinhood 3.0-RC1 as our little compute client, even though the server was the Robinhood 3.1 version. So I was kind of looking at minor version changes between, the Robinhood server and one of these HPC compute clients. And within the close versions that I had, I didn't see any version difficulties. I got the same error messages on the Robbie client query that I got from, any other version. There was no difference depending on what Robinhood version I had on my client. So again, our issues are those little nuisance messages. I said I'd like to see if I could do something a little better about that so my users don't necessarily say, but I had an error. The biggest concerns we have about this right now, from our point of view, is the security. Our current method for using the Robbie read-only access to this Robinhood database from an HPC compute node is that, one, if the user happens to, cat a DB password file, it's not hashed, it's read-only, but it's sitting there in a .db file if they know where to look. And the more important one is that we have not yet implemented any cell security on our Robinhood database. And there are cases and times in which we really don't want one user to look at another user's things. So one of our highest priorities that we're trying to do in, hopefully the next even month or so, is to use the database ability to provide some level of cell level security so that, it would see if it was even able to read that particular information and return it. I've not gotten deep into this yet. I am not a DBA, and I'm not sure how it would react, being that we are using one and the same Robbie read-only client to do this. I'm not sure how we would have to pass any credentials in. So that is our currently most serious issue with just enabling this Robinhood query ability on our compute nodes. I have not yet tested this under a full user load. I have not yet incorporated the user feedback. And the last one, we had an issue with responding to an LFS data version check. And again, that turned out in our case to be kind of a benign error message, just the way the version check was being done in the HSM part of Robinhood. If a file was 0 length, it would just spit out an error to our Robinhood luster.log file. And I think we may have gotten past that with a newer version of some of the software we're using. So I'm thinking that last one might be fallen off our screen here. So those are the current issues, and as I said, security is our big one. Further work is to address the cell security in the database, see if we can get that something that's still quick and manageable. Can it still work with our Robbie read-only client? And we need to expand testing under load, see if our Robinhood server can actually deal with hundreds or thousands of compute nodes which may be making queries simultaneously or very close together. We want to get use of the user extended attributes more cleanly. We'd really like to see if we can leverage Robinhood to do that. The Robinhood report is nicely written, nice little case statements and stanzas, and you can have something for handling a different X attribute. We just have to find out where in like the .h type of file and stuff we need to set up our struct for our XAdder table that we added to our Robinhood database. So that's something we'd like to get going so we can leverage the power of Robinhood and its commands to include the user extended attributes. Again, cleaning up the messages a bit. And we want to see if this will work when our Robinhood is monitoring more than one Lustre file system. We know that we can have a single Robinhood server that monitors more than one Lustre file system, and that you can make queries on it by specifying, a -f option and the configuration file for that particular file system. But we're interested in knowing if there would be a load issue if we add this kind of compute node query function to our server. Does that add enough load so that we're not able to monitor more than one system? Or if we're monitoring more than one system, can we apply the same kind of Robbie read-only password to both Lustre file systems and just have both of them work? That's something we're going to be looking at down the road. So I'm perfectly open to ideas, things of which I've not yet thought of, things which maybe can be better planned than the way I was viewing them with perhaps my myopic viewpoint. So I want to thank the people who helped work on this project with us. We had Joe Houlihan from BAE. He was our database guru. He has since retired. Thank our Site Lustre team. I am very grateful to the CEA Robinhood team for their software product, and I am also very thankful to the Lustre team that we have a storage system that is queryable and we can get the metadata through change logs, and that's just a really useful storage system that, hey, I didn't have to write. So, and I also like to thank Michael Fitzpatrick at BAE for helping get some of these the slide things organized for me. So that's basically it in a nutshell. If anyone has any questions.
Back on the further work slide, I could at least tell you what I've run into and whether that helps or not. Yeah, the cell security, I mean, I think I've come to the conclusion that we don't really care if people can see each other's, but that was going to be my question was, I figured you might care more who can see whose metadata. But I don't and I'm not the expert here, but I don't think you would, if you couldn't use a single database ID to be able to, because you have to have some way to authenticate that user that's querying. So I think you'd want to tie your user's authentication scheme into the database authentication scheme to be able to, split out who can see whose metadata. Just a guess on that, but I think for the var log stuff, you can specify in the Robinhood config file where that var log, where the log files go to. So you could probably just in your configuration just set it to dev null for each of those files. Is a quick hack I could think of. And for the Robinhood stuff, maybe it's because I'm using really old servers for our Robinhood, but we've had pretty good success. One Robinhood server, one database server per file system. You get kind of your linear scaling there, and then you can aggregate that information, in your front end. For our case, we do the web front end, or actually we wrote our own web front end for aggregating that. But I think for your case, if you're doing the command line stuff, there is switching to say which config file I want to use, and each config would be, so you either write a wrapper script to help users aim at the right Lustre file system, or teach them how to use that flag. And but it's good to see. I mean, we're not in the couple billion file range. We're in the tens of millions. So we're at a different scale, but it's good to see that Robinhood continues to scale for folks.
We're looking at a couple of different things, like whether or not we'd have to pass like a Robinhood ID and maybe have like a SID, Robbie dot, my ID or something like that, and do some parsing in order to work cell security. We're not sure. We're also thinking that now that Lustre is capable of mounting, subdirectories underneath, we could just say, users can have, these directories that are there into this space or this Z pool into which they can write, and then just, have the security done, basically at a Robinhood table that was maybe for a mount point, but that would mean we'd have a Robinhood table for a Lustre mount point, which is now /foo/bar. So that's something else we could think about. We're not sure, instead of the one overall Robinhood mount point, we have a sub-mount points and do a different Robinhood for each one, which would mean even though our Robinhood server was doing one mount point, it would have tables for various, subparts of the overall mount point, because we would be mounting them as, individual Lustre mount points from a larger group. So there's still a lot of, thought, and I think that until we actually get some users driving this and pounding this a little bit, I'm not really sure I can evaluate which would be a reasonable solution until we see how people really want to use it. And that's, part of the further work there.
Any other questions?
Could you speak a little bit about your underlying storage for your database on your Robinhood servers?
You mean like Lustre version or hardware? Or?
Actually, what the database is sitting on itself. Is it sitting on a rated SSD? Or?
Oh, yes. You're very good question. Excellent question. The database of the Virtualized MySQL on our Robinhood servers is actually on tuned NVMe hardware. So we have that on our Robinhood servers. We went in and did some of the tuning on it. And yes, so we do have our Virtualized MySQL on NVMe space.
So I'm actually curious to ask a question. So when you do a full initial scan, how long does it take you to get 2 billion records into the database?
That took us, like, trying to think, it was almost exactly the same time of one of the earlier presenters, because I remember seeing it earlier in the week. I went, gee, that was the same amount of time it took us. The number is escaping me right now. It's like 2 days, was it?
Okay, great, thank you. All right, well, let's
But I was
thank
happy to see that he was getting about the same time we were getting.
Okay, well, let's thank our speaker.
And this is next and previous. Okay. Okay, hi, I'm here to talk about the Lustre Irods connector. It has some things in common with Robinhood, but we're solving a very different problem than what Robinhood is solving. Irods is a data management system used throughout the world, and we've had needs to integrate Lustre with Irods, and so that's what this connector is doing. A little bit about Irods. Irods is an open source BSD3 license. It's distributed. You can run Irods on your laptop. You can run it on a cluster of thousands of computers. It's metadata driven. We like to say that everything is actionable through metadata. You can drive your workflows through metadata, and so metadata is a very important feature in our system. It's data centric. So actions depend on the metadata in the system. First off, I need to back up a little bit and talk about the metadata in Irods. Irods does have system metadata, like you see in Lustre, but a lot of times when we're talking about metadata, we're talking about user-defined metadata, and that's a big feature that Irods has. Users can attach metadata to any of the first-class objects within Irods, the data objects, collections, users, everything can be attached to metadata. And the system can also, through the rule engine, can automatically attach metadata to data objects depending on, or collections or anything, depending on what's in the files, whatever you need. Okay, so we'd like to talk about Irods as an integration layer. So Irods integrates your existing storage, your compute resources, maybe your indexing services to your Irods clients. The Irods clients we have iCommands, which are command line interface into Irods. WebDAV, we have web-based interfaces so that users can navigate all their collections, data objects through Irods, through the web. Okay, the most obvious thing that you'll see in Irods is virtualized data virtualization. And what we like to say is that we abstract all your data in your system from the user and gives it a common namespace, a virtualized data system, so that the user doesn't have to know the intimate details about all of the data within your system. It could be just a Unix file system, Lustre, could be object stores, web server, Amazon storage, things like that. And the user doesn't have to know the details about the storage or the replication within the system. So as we say, we provide a logical view into the complex physical representation of your data. So here's an example of the data virtualization. Within the box, you see that we have kind of our virtualized file system within Irods, the virtualized namespace, and underneath it, you see a bunch of Irods servers. One of the servers is a catalog server that has a connection to the Irods database. You can now have multiple catalog servers and then resource servers as well. The example we show, we have a data object, which is basically a file. We call them data objects just within Irods that has replicas, 3 different replicas within the system. Users can see those replicas, but they don't have to. They don't have to know when they're getting or putting a file where the replicas are going, or where the files are going and being replicated. So we like to say we project the physical namespace into the logical. Another thing is the replicas provide durability and locality of reference. So if a user is connected to a certain resource server, Irods has resource servers. Each of them have 1 or more vaults underneath them. And if a user is getting a file locality of reference is usually the primary decision maker of where the file is being gotten. But also it provides fault tolerance as well. The other thing is data discovery through metadata. So one thing we've discovered is when you have millions and millions of files, researchers and institutions need to be able to find the data files that they want. Having file names and putting things in a certain directory just isn't enough when you have millions and millions of files. So we can put metadata on these objects, and that allows you to discover what you have. And the metadata can be generated automatically based on what is in the object when it was ingested. Basically, the rules that you have can automatically populate metadata on the file. And metadata can be attached to any first-class object within iRods. So not just, I talk a lot about data objects because it's the obvious one, but collections, users, storage resources, even your zones can have metadata on them. And metadata makes everything actionable. Your rules are generally driven by what is in your metadata. So you can assign metadata to a resource that says what the capabilities of that resource are. So here's an example of an iRod system with the metadata on the resources, metadata on the user, collection, and files. So an example would be metadata on the resource could tell you what capabilities are in that resource. Is it a high-performance computing, with a lot of compute nodes? Is it a HIPAA-compliant resource? Your policies can be different for that, and the metadata on that resource can tell your rule engine how to treat that data. It could be long-term storage resources, things like that. So I'm giving an overview of iRods first, just to let you know, and we're going to get into the Lustre connector and how this all connects into Lustre in a minute. Okay, the rule engine. iRods has a rule engine basically that it's basically a scripting language that when you get policy enforcement points are executed within iRods, you can write code at the point of those policy enforcement points to do whatever actions you need to do. So you can control authentication, you can control where things are stored, and there are policy enforcement points for basically all actions within the system: authentication actions, storage, any kind of database access. So the rule engine originally was a specific iRods native rule engine language. Now we support many different languages: Python, C++. So if you want if you want speed as your main concern, then you would write your rules in C++. So again, the iRods rules can do really anything, but common things are restrict access to objects, logging for audit purposes, reporting, provide additional context for the objects, and even like send a notification that someone ingested some file in a certain location. We have policy enforcement points. There always have a pre and a post policy enforcement point, and so you can attach your code to those locations and do whatever you need to do at that point. So here's another example of a policy enforcement point of doing a data object put. And when you put that data object, you'll run the data object put pre and then data object put post. But that operation will expand into a few hundred policy enforcement points. So you can, depending on what your need is, you can catch any one of those policy enforcement points and do whatever it is you want to do. If you don't want to do anything, they're just no ops. They won't impact your performance at all. Okay, collaboration. Different institutions can collaborate with iRods and connect their clusters together. All you need to do is share a secret key, add some users to connect users in the system, and permissions, and they can start collaborating. And then you don't need to pre-plan any of this. They can just, as needed, you can set up the collaboration and then tear it down whenever you're done. So we like to think of iRods as a interface layer to your storage, to your audit services, your indexing services, your metadata, your compute resources, your authentication resources. It's very easy within iRods to, storage is kind of built in with different storage plugins. The audit services, we have an audit plugin that will basically write out all the policy enforcement points that you execute. And by doing that, you can audit everything that happens within your system. You can write it to a database, and that helps you know what's going on in your system. Maybe for compliance reasons, you have to have that audit. Indexing so you can find things easily. And these all can be added on to iRods very easily, just a few steps. Here's another example of federation within iRods. So we're federating multiple zones, and they're sharing not only data, but they're sharing all the services underneath. So an example would be that one institution needs to do compute on resources from another institution. So you can send the data from one institution to the other institution that does the compute and return the results. Or you can integrate other services between the different institutions. Okay. So this is basically kind of end-to-end, like telling the whole story about the data. That's what iRods gives you. Anything from metadata ingest to publication to retention. One thing we have, like a lot of government rules around retention policies on different research. Like in England, they all the research data has to be stored for 10 years. And sometimes, in some cases, even has to be stored 10 years after the last access of the information. So the iRods rules allow you to kind of work through that life cycle through the system. And you can add a persistent identifier to all your objects through metadata, and so that you can track what has happened through the system through time. And here's an example of iRods. Objects are landed in a landing zone and put on a resource there, but those are tagged with metadata that says they need to go to some compute services. So they're sent to a compute resource, and where it has a high performance computing in it, and that can compute results, add metadata to the results, and send it back to iRods. Okay, so that's kind of a general overview of what iRods is. So now I'm going to talk about the Lustre framework, the connector is what we call it, the Lustre iRods connector. So, one thing we found is users want all the features of iRods. A lot of our users have Lustre and they have iRods, and they want to integrate those two together. They want to keep the features of iRods, but also keep native access to their Lustre systems. Now, Irod's already supported Lustre as far as a vault, which is a storage within Irod's. Any POSIX system can be your vault. So you could always have Lustre system as a vault within Irod's. But that has some drawbacks. One is that Irod's, when you put something directly in a vault, Irod's wants to be the manager of it. So it doesn't want people to change all the files underneath the file system. It doesn't know about them if you don't go through the Irod's APIs. So that's not, for a high performance parallel file system, that's probably not what you want. You want to be able to have users have direct access to their file system and just let Irod's know about all the changes that happen. Also, you don't want to have to necessarily rewrite all of your clients to use the Irod's APIs. So the thing we solved with the connector is you can connect directly to your Lustre file system. All your computing, everything can be directly in Lustre, and we'll ingest those changes within Irod's and attach metadata to everything that you want. And so users can use the Irod's APIs when it's advantageous to them. If they want to search for data through metadata, they can go through the Irod's APIs, but they don't have to use the Irod's APIs all the time. So we'll detect changes. The design of it is users can directly access their file system. We use the Lustre changelog, similar to Robinhood, to keep Irod's in sync with the Lustre file system. All catalog updates are in place, registrations, which means that we don't copy data. We're not in the data path at all. So we will not impact anyone's performance. We just register the changes within the database. Efficiency considerations that we considered when making this connector is we accumulated and aggregated changelog updates so that we send fewer information to the Irod's database. It's multi-threaded, meaning that once we've accumulated the updates, we send the updates to Irod's. We send batch updates to Irod's, and then Irod's, each thread can send to a different Irod's server and wait for a response. We have all the dependencies worked out so that all the updates, even though it's multi-threaded, the updates will still be performed in an appropriate order so that Irod's database is all updated appropriately. So we have a plugin within Irod's that will receive these batch updates and do batch updates to the database. So we can scale with multiple Irod's endpoints. The key there is you want a database that's distributed and so that you can make multiple updates to multiple updates to multiple Irod's servers that all connect to a distributed database. Otherwise, if it's just one database, a lot of times that's your bottleneck. So here's kind of just a little overview of what we do. So we read Lustre changelog. We have a poller of the Lustre changelog. We aggregate the changes and have multiple threads that send updates to multiple Irod's servers. And a plugin that's sitting on Irod's that are receiving those changes and making the appropriate updates. Okay, the Irod's API plugin is a dedicated plugin within Irod's that accepts the bulk updates. There are two different modes for the Irod's API plugin. One is direct mode and one is policy. I talked earlier about all the policy enforcement points that are executed within Irod's. And if you have policy enabled, you will go through the Irod's API and do registrations within Irod's, and that will force all the policy enforcement points to execute. If you have direct enabled, then you're just doing direct database updates within iRods. So that is the case where you want to prioritize efficiency over policy. So you're just doing batch updates to iRods. So here's a little quick example of using the connector. First, I showed just mounting the Lustre file system on the server that has the connector. The iRod server that has the resource that you are defined as the resource for that connector, or resource for those Lustre files, also has to have the same mount point on it. So if those aren't the same server, you have to have the mount point on both the resource and just the one resource, not all the resources, but one resource and the server that has the connector running. So what we do here is we mounted the file system. I left out a few steps of running the connector as a service. And then I just created a file. I did a quick ILS and showed you what was in iRods, the in-temp zone Lustre DR1. There was nothing there, and then a second later I did another ILS, and you'll see that the file has been registered in iRods. I can get, through iRods API, I can get the file information. I can also list the metadata on the file. The Lustre identifier is one of the metadatas that the connector automatically writes so that it can track the Lustre object to the iRods object. Then I move the file within Lustre, and I do another ILS, and I see that the file's been moved within iRods. The file hasn't been moved. The file has been registered at a different location within iRods. ILS, I didn't talk about that. iRods has icommands, which are very similar to Unix commands. ILS, iPut is like a FTP put, things like that. There's probably 40, 50 icommands that let you interact with iRods just through the command line interface. So here's an example of the Lustre configuration. I mean the configuration of the connector. So a couple things that this demonstrates is that some things that Lustre specific things that we have to give the connector is the MDT name, the amount point that's available to iRods, so that when iRods interacts with the objects, it has to know where to find them on the system. The registration point in iRods. So right now we map all, iRods has a logical namespace and path. So we map all of the physical paths directly from the mount point to the registration point within iRods. In the future, we want to make that a little bit more flexible so that maybe objects that belong to certain users can be mounted to their, or can be registered in the user's home directory within iRods, and also add some user modifications within iRods so that we can maybe directly map a user in Lustre to, on the file system to the user in iRods. That's not been done right now. So right now everything is registered at a specific location. But then you can then assign, give it access through the iRods APIs to different users who are using the iRods APIs to access these objects. And also just show that we have multiple iRods endpoints. So you can set up any number of threads that will do the updates. Each of those threads can be assigned to a different iRods endpoint, so that you can scale horizontally when you're running the system. Okay, I'm going to change topic a little bit and talk about the automated ingest capability in iRods. This is not specific for Lustre, nor does it use the Lustre changelog or anything like that. We also have a tool that does a parallel walk of file systems, determines differences between those file systems and iRods, and does registrations within iRods. And so this has two purposes. One is onboarding your existing data into iRods, and another is disaster recovery. Let's say you're reading the changelog for your Lustre files, and you want something goes down, something doesn't work, you missing changelog records or something because something crashed, then you can run this automated ingest capability to synchronize your iRods registrations with your Lustre file system. And we've run this with distributed database, CockroachDB, and have gotten really good performance out of it. I have not yet connected the iRods connector to Cockroach, but that is the next step that we're going to do. Okay, so the key here is for performance, we wanted to make everything parallel front to back. Obviously, we have a parallel file system. iRods, we have multi-part data transfers that's coming very soon. It can allow you to transfer files in parallel. We now have plugins for distributed databases, specifically CockroachDB. And we also have the auditing and indexing framework. Okay, so Cockroach, that was the latest database plugin that we've written for iRods. It's a distributed database, but it supports an SQL-like interface. With Cockroach, you can now have multiple catalog service providers. The catalog is the resource within iRods that has the connection to the database. That used to only be one resource that could be the catalog service provider. But with Cockroach and some changes within iRods, you can now have multiple catalog service providers. And that's really important for the Lustre connector, because if you don't use a distributed database, then that's your bottleneck. You can send batch updates to 10 different resources, but especially if you're doing direct access, direct database updates, they all have to be redirected to the catalog service provider. So you really need multiple iRods, iCat servers to get the full horizontal scaling of the system. Let's see. Okay. I was going to do an online demonstration, but it wasn't really going to be possible here. So I updated the slides just to kind of show you a quick demo of the use of the connector. So in this example, I have a Lustre mount point. I copied 1,000 files into Lustre. I did a couple ILSs just to show that the files are there, are registered there, and the collections are registered within iRods. And I did a command called iQuest, which is kind of an SQL-like query to query the iRods database, and just to show that I have 1,000 data objects within iRods. And that happens just very fast. Okay, another example is I enable the policy instead of direct database updates. I enable policy so that all the policy enforcement points are executed within iRods. And I updated an iRods rule, the AC postproc for file path register, which is all the files within the connector are registered within iRods. So I updated the rule to read out image metadata on the files, or the image information from the file, and write it to iRods metadata. It's not the best example because I'm doing an MSI execute command, which runs an external Python process to get the metadata from it. In a real system, I would use the Python rule engine and write everything directly in Python or C++ or whatever. But I just wanted to demonstrate that, this just a demo on how you can automatically get metadata from objects that are ingested in iRods. And then I did I copied a JPEG file into iRods, and then I did an imeta ls command to see to look at some of the metadata that was in iRods. So you have some image metadata information, and the Lustre identifier as well. And that's it. Any questions? Yep.
Do you have any questions?
So I'm curious if you've got a general concept of how fast you can read changelog entries?
We do not right now. It's being tested at the moment at the Texas Advanced Advanced.
Heck.
So most of my development was just on VMs, so it's not really a good test on the performance.
And then looking at your config, it looks like you thought MDTs were tied to mount points, but MDTs kind of aren't tied to mount points if they're multiple in a file system. Do you care about that? So with D&E, we can have multiple MDTs in one
Right.
mount point. Do you deal with that?
No, but that is something we want to look into and make sure that we can do that. That's actually something I was looking into the other day.
Any other questions? Okay, well, thank you.